much for output systems.
Okay, thanks a lot for your kind introduction. And before I go through the details of my presentation, let's have a look at the brief contents. First of all, I want to start with fundamentals of sliding mode control for nonlinear dynamic systems, especially for single input, single output cases. And these will further on be extended to the case that we have interval uncertainty in the dynamic system models. And afterwards, I will show you how to extend these sliding mode techniques also to backstepping type controllers for nonlinear dynamic systems. And after some examples, I will describe extensions that are necessary for the case of multi-input, multi-output scenarios. Now, for the basic scenario in this presentation, we consider that our nonlinear dynamic system is given in nonlinear controller canonical form. And this is described, as you can see on the slide, by a chain of integrators here for the first n-1 state variables, and the nonlinearity is given in the last time derivative here in the variable xn dot, the last entry of our state variable. Okay, there we have dependencies in the state equation here, depending on a nonlinear way on the states x and also on some system parameters. And these system parameters are assumed to be bounded afterwards by intervals. Now, a fundamental requirement for controllability of this system is, in my opinion, quite obvious. This term b here has to be definitely not equal to 0, because otherwise you lose controllability and the control procedure is not applicable then. Okay, this has to hold for any admissible operating point for the states x and for these bounded system parameters p. If this is given, it's quite easy to design a feedback linearizing control strategy. What you have to do then is you have to compensate the nonlinearity here with a negative sign here minus a, and introduce some virtual system input u. And this virtual system input u will now, on the following slide, be the control input with which we design for this integrated chain of length n, the feedback linearizing and guaranteed stabilizing control strategy. Now, for those of you who are familiar with differentially flat systems, this is a trivial case of a differentially flat system model here given on the slide. Now, if we want to design a first order sliding mode control strategy, what we have to do is we have to specify the goal of our control design. And the goal should be that we have a given reference trajectory for the first state variable, that's x1 desired, and the actual system state x1 should become equal to the desired system state. And the same has to hold for all time derivatives up to the order n of this desired trajectory. Now, the first prerequisite here in this case is also obvious. The desired reference trajectory has to be n times continuously differentiable in order to make sure that we can find such a control strategy. Now, we can design some kind of, first of all, you could say sliding manifold, or you could say a measure for the tracking error in such a way that you define a weighted sum of the output error itself and the first n-1 time derivatives. And it can be shown in order to guarantee asymptotic stability of the system on this goal of the control strategy, that these coefficients alpha r here in this so-called sliding surface, they have to fulfill the necessary and sufficient criteria of a Hurwitz polynomial of the order n-1. Okay, if this is guaranteed, what you have to make sure is for states that are not located on the goal, you need some asymptotically stable motion towards the desired operating conditions. And this can be achieved in such a way that you specify a Lyapunov function candidate, like it is written here on the slide, as 1/2 times s squared, and s squared was this expression that I introduced on the previous slide as a measure for the tracking error. Now, in order to make sure that the system is converging towards the desired operating state that is given by s equal to 0, you have to make sure that the first time derivative of this Lyapunov function candidate is guaranteed to be negative. Okay, if you plug in the definition here of the sliding manifold, you end up with this expression here. And in order to simplify the control design, what you can do is on the right-hand side, instead of writing that a time derivative should become negative, you could say that our design criterion is something slightly more strict in this case. You have a positive constant eta, and the left-hand side of this inequality should be guaranteed to be less than some minus eta times the absolute value of this error measure. Now, if you specify it like this, what you can do is you can plug in again the definition of the sliding manifold S, and then you can solve here this expression here for the control input, and the control input is involved here in this time derivative of the order n. That means the last time derivative of this integrated chain that we had on the very first slide of the talk. Now, if you're doing this, you end up with a control strategy, and this is nothing else than classical first-order sliding mode control for nonlinear dynamical systems. You end up with a control strategy U that depends on, there's some dynamic feed-forward control, you could say here, on the sliding surface, and in cases that you're not exactly located on the sliding surface, you're activating a variable structure term, which depends on the sign of the tracking error. Now, what we want to do is on the following: we want to extend this control procedure in such a way that we develop some interval version. Interval version in such a way that we take into account uncertainty in the system parameters P, and that we take into account also uncertainty in the measured or estimated state variables. And yes, what you will see then afterwards is we end up with a control that is itself an interval variable. Okay, it's obvious that you cannot apply an interval variable as the input to a dynamical system. We have to think about criteria, how to implement this, and yes, how to select a point value system input from the computed interval control strategy at the end. And this is what you see on this slide. The first thing is, since we cannot usually measure the states with absolute accuracy, you have an interval definition of the tracking error, and what you can see in this equation is that the actual system output, which is usually measured, and either the measured time derivatives or reconstructed time derivatives, they become interval variables here, denoted here by the square brackets. And this also means that these tracking errors and the corresponding time derivatives of the tracking error signals, they're included again in some intervals. And as before, we have to plug in this information in the definition here of the sliding surface given by this equation here. And our goal remains the same. We want to make this equal to 0. Now, as I already mentioned here for the fundamental control approach, these coefficients here, they were chosen as a Hurwitz polynomial of the order n-1. That means as soon as we have reached the control goal, that means that each of these derivatives here, theta psi tilde here, if each of these derivatives become equal to 0, we have ensured asymptotical stability. Now, the interesting part is what is happening when we're not on the sliding surface. When we're not on the sliding surface, we're taking again our Lyapunov function candidate that we had, and we want to make sure that its time derivative becomes negative. That's the same as in the point valued case. Now, what you can do is you can follow the previous control design procedure and plug in the uncertain system model here, depending on the uncertain system states X, depending on uncertain system parameters P, and your interval definition of the sliding surface. Okay, obviously, this control strategy is only defined in the case when you're not dividing by 0. That means that's the same controllability prerequisite that we had for the fundamental control law. And the other thing, what you immediately see is, in the numerator of this expression, and also in this expression in the denominator, we have interval variables. That means that the control signal itself becomes an interval. Okay, this interval is chosen in such a way that the time derivative of the Lyapunov function candidate is guaranteed to be negative. Okay, now what do we have to do with this? We have to take the bounds of this interval, select either the infimum or supremum value of this, and depending on the sign of B, either rounding inwards or outwards, and select the corresponding candidate, point-valued candidate then, which is guaranteeing that the Lyapunov function candidate has a negative time derivative. And this is the actual control law. And this is guaranteeing asymptotic stability for the actual system state X, which makes sure that we are converging towards the desired sliding manifold. And that's an interval-based control strategy here when we take into account something that is equivalent to a sliding mode. Okay, what is obvious here in this case? We are evaluating a sign function of something that is uncertain. In the near surrounding area of our control goal, we're usually not able to distinguish if the control error is positive or negative. That means when the sign function is deactivated, when we cannot specify the corresponding sign, that means the sign function just becomes equal to 0 in this case, and we're just using the regular control strategy here on the left-hand side, which is just a dynamic feed-forward control in this case. Okay, now we have seen that we can guarantee that the aerodynamics is asymptotically stable, and what we want to ensure now is, if we have some tracking errors, we want to make sure that we don't violate constraints on the state variables. For example, we have some reference trajectory, let's assume that's a position of a dynamical system, and we want to make sure that the actual system output does not overshoot the specified reference trajectory. Okay, for that case, we have to integrate some barrier functions. These can either be one-sided strict barrier functions or two-sided barrier functions which specify a lower and upper bound on either system outputs or state variables. And these bounds can be included directly in this control framework. There I want to advertise a little bit about a book that I published last year together with my colleague Louisa Senkel. And yes, there you can also find extensions, for example, to second-order sliding mode control strategies in there. And yes, a more detailed derivation of the theory behind this. Now, let's have a look at these constraints. These constraints are formulated as some kind of repelling potential. And this can either be done here in the one-sided case by this logarithmic function. And this logarithmic function makes sure that as the tracking error is something that is always below the desired reference trajectory. We want to make sure that we don't overshoot here the reference. Okay, if we are adding this to the original Lyapunov function candidate, we have to make sure that now the extended Lyapunov function has a negative time derivative. And this is what you see on this slide here. The extended Lyapunov function candidate has a time derivative that corresponds to the original derivative plus some correction term. And what is obvious, this term v dot that we had in the original control design, this must have dominating influence in the neighborhood of the operating node. When we're far away, this repelling potential can take over and has to ensure that we don't violate the state constraint. Okay, now we can follow exactly the same derivation procedure that you had seen on the previous slide. And yes, what you see already, you have the original time derivative expression plus some correction term here. And there's one problem that you will see afterwards in 2 slides. Before we come to this little technical problem, we have a closer look at two-sided state constraints. They can also be formulated here by logarithmic functions, but the only difference to the previous thing is instead of an odd power, we now need even powers which have something shaped like this. We have two-sided repelling potentials which lead us into the desired operating range at the end. Okay, when you're calculating the time derivative, you end up with the same structure, the original v dot plus some correcting term. And this has to become altogether strictly negative at the end. Okay, now we're coming to the problem that you may have recognized already 2 slides ago. I'm going back here to this expression. The problem is this term 1 over s. Our goal is s equal to 0. That means we have to make sure that as soon as s equal to 0 has reached, this term must be regular. Or in other words, we want to switch off this correction term. Okay, how can this be done? This can be done in such a way that we are replacing this 1 over s by this rational expression here, which is a good approximation for 1 over s if s is significantly larger than 0. And in the case that s is becoming close to 0, it is just deactivating this part. Why can we do this? The reason for this is we want to make sure that the original control goal, s equal to 0, is not modified by this repelling potential. Okay, and in other words, also the deactivation of the variable structure control part is happening for s close to 0 due to the fact that we cannot specify the sign of the tracking error there due to interval uncertainty. Okay, that means we don't have to care about approximation errors that appear in this case when 1 over s comes close to the point where this is not defined, and for s equal to 0, in any case, this variable structure part is just deactivated. Now, let's have a look at a simple application scenario after going through the corresponding control strategy. The defalsification of the control strategy is done in the same way as before. We're choosing either the infimum or supremum of this interval, and this is being applied to the actual dynamical system. And this holds for both cases, either for the one or for the two-sided output constraints. Now, let's have a look at a simple application scenario. Let's assume that x1 is the position of a point mass, x2 is corresponding velocity, and x3 should be an input force, which is generated by some actuator that has an underlying dynamics. Okay, and this underlying dynamics of the actuator unfortunately has the property that parameters of this are uncertain. These parameters P1, P2, and P3 can vary in the corresponding ranges, and as you see there, due to the change of sign, this includes unstable dynamics. Okay, the controller has to stabilize, first of all, the unstable dynamics of the actuator and has to make sure that the position x1 tracks some desired output profile. And this desired output profile will be seen on the following slide. First of all, I specify 5 cases, and these 5 cases that I want to specify are Lyapunov function candidates that either take into account the state constraints or not. Okay, going through these details, when we deactivate this overshoot prevention, that means this extension here with the logarithmic function, you see that the actual system output is overshooting the dashed reference trajectory. If we're activating the corresponding barrier function, we prevent overshooting, and this holds either in the case that the parameters are exactly known, this is what is given on this slide, or it also holds for cases when the parameters and the measured system states are uncertain. And furthermore, we can show that also deactivating a two-sided state constraint leads to potential violations here on the right-hand side, and activating the two-sided state constraint leads again to some feasible system outputs. Now, what you have seen there is a control strategy that works very well in cases that your original system model is given in this nonlinear controller canonical form. But usually this is not the case. It's more often the case that you have something like the strict feedback form here. This holds for many electromechanical systems that are given in this case. And this strict feedback form is defined in such a way that you have dynamics for a state variable, let's say x1, and this depends just in an input-affine manner on some other state variable x2. The dynamics for x2 depends on x1 and x2, and again in an affine manner on a third state variable, and so on. That's more or less something like an onion-like shape. You go from shell to the outside here, and as what you want to do at the end is you want to design again a stabilizing control strategy for the actual system input, which is denoted by V in this case. Okay, obviously these equations must be guaranteed to not be decoupled. That means all of these expressions, B1 till Bn, must not be equal to 0. And this must hold for uncertain states and also for the uncertain system parameters. Now what you can do is, for each of these differential equations, you can specify as before a Lyapunov function candidate. And this Lyapunov function candidate takes into account deviations between the jth system state and its corresponding desired trajectory. Okay, one option is to design these Lyapunov function candidates just here by these quadratic expressions. Then it's easy to calculate the corresponding time derivatives, and these corresponding time derivatives have again to be strictly negative. Okay, if you have a closer look at these expressions, what you will see is if you're calculating Vj dot, they depend on some derivatives here of these state variables that entered the original system model here in the affine manner. That means if you're treating this x2, x3, and so on as some artificial or virtual system inputs, the backstepping control design, these must be differentiable expressions, and hard switchings, like in the sliding mode control strategies, are only allowed for the actual system input, for the physical input V. And this is what you see on the following slide here. The corresponding stabilizing and perfectly tracking control strategies are characterized in such a way that you design some desired expressions here for this affine variables in the state space representation. This representation is motivated by the variable structure approach, and you will see on the following slide that this saturation expression here is a differentiable expression here for the orders 1 till n-1, and for the highest system order, for the actual control input, you can specify a hard switching there. Okay, and the design of the control strategy for the uncertain case, that you have uncertain system parameters and uncertain measured states, is being done in the same way as for the original variable structure control approach. You're plugging in the corresponding interval variables, and you're selecting either the infimum or the supremum of these expressions here, the one value which guarantees the asymptotic stability. And this is something that you will see here in the following for a second application scenario. First of all, again, I want to point out what is happening in the close vicinity of the control goal, where this argument of the sign function becomes equal to 0 in cases when you cannot distinguish if the error is positive or negative. We're using the third case here, the case that we're switching off the variable structure control part. Okay, now let's come to a slightly more complex system model. The slightly more complex system model is that we have some kind of inverted pendulum. That's a pendulum arm mounted on top of a carriage. The carriage can be moved in horizontal direction, and there's no actuator here at the joint that is depicted here, and our goal is to move the carriage in such a way that the pendulum is held in an upright position in the unstable equilibrium. Okay, modeling of this system is quite easy. You take Lagrange's equations of second kind to derive these corresponding state equations. And what we want to do now is we want to apply both control strategies. Okay, both control strategies were designed for system models where the states are given in such a way that we have a desired output and time derivatives of the desired output as state variables. Okay, what we have to do in this case, we have to specify the system output as the horizontal pendulum tip position and calculate the corresponding time derivatives. These are the corresponding d derivatives of the system output into the direction that is specified by the vector field of the state equations. Okay, what you see there is a small problem. The second time derivative here already depends on the actual system input, on the input force. Okay, that means this system output y is definitely not the candidate for flat system output in this case, and without any further approximation, we could not use this as the corresponding state variable to be controlled. Okay, there's one way around this. The one way around this is we are neglecting the influence in such a way that the complete approximation errors are over-approximated by corresponding interval parameters. These are parameters P1 till P4, and they can be included. Unfortunately, the expressions are too long here for the slide. They can be included in the highest order dynamics for the variable structure control design, or they can also be included here in the second and third state equation here when we want to use the backstepping type controller. Okay, details can be found later on in a paper that I'll write corresponding to this presentation here. Now, let's have a look at the simulation results. If we're using the pure variable structure control strategy, the extension of the sliding mode, what you see is, without activating the Beria-Lyapunov approach, we may violate some upper state constraint. And this can be prevented by activating the corresponding Beria function. When you're zooming in here, you see that the worst case output position is guaranteed to be below the corresponding state Beria. And this holds despite uncertainty in the system parameters and despite uncertainty in the measured states. Now, what we could also do is we could use the pure backstepping type control strategy. And this pure backstepping type control strategy leads to scenarios when activating, again, the two-sided barrier function, leads to trajectories that are feasible in such a way that the corresponding pendulum tip position is included within the response. But you have some oscillations there. Okay, now what could we do? We could switch as soon as we have reached the goal as equal to 0 for the very first time. We could activate the variable structure control approach. And in that way, we can just benefit from both advantages of the control strategies. The backstepping type control strategy is usually easier to parameterize to get fast dynamics. And the variable structure approach with generalization of the sliding mode is more easy to parameterize in such a way that you get more or less steady-state accuracy. Okay, and this is what you see on the slide. As soon as we have reached the goal, we are switching from one strategy to the other and stay with the variable structure approach. And this prevents the remaining oscillations here. Now, you had seen in the title of the talk, I want to perform generalizations to multi-input, multi-output systems. And these are, if you have understood what I did before, quite easy. The generalizations are, if you want to perform a sliding mode design, first of all, instead of a scalar system input, you have a vector value system input. And this is being coupled here by an input matrix B, which may be state dependent. Okay, it is very easy to design a variable structure controller in cases that you have decoupled Caesar systems in fact. Okay, then you have just to design for each of the outputs and each of the inputs the corresponding single input, single output controllers. Okay, this is trivial, we don't have to discuss about this. Okay, the more interesting thing is cases where we have actually couplings. And there, the corresponding prerequisite or the regularity assumption to be able to find some kind of equivalent control strategy, that means a control strategy that ensures perfect trajectory tracking for cases that you have vanishing control errors, is that this partial derivative of the tracking error signal with respect to the states times the input matrix B, this is a regular matrix. And this was something that was already published in the 1970s in several publications of Van Woodke. And if you're doing something like this, you can easily generalize this interval-based control strategy in such a way that you're extending the Lyapunov function candidate to a vector-valued formulation, that for each of the system outputs, you're specifying the corresponding sliding manifolds, and each of them is being included here in the Lyapunov function candidate as a square function. And then we have to make sure that for each of these summons, okay, there's a sum missing here on the right-hand side. Okay, it should be a sum from 1 till m, summing up over all inputs. This expression here must be guaranteed to be strictly negative. That's a straightforward extension of the single input to the multi-input scenario for the sliding mode control strategy. Okay, there are further possibilities, and these further possibilities come from the fact when you don't have a system model that is given directly in strict feedback form or in this multi-input, multi-output nonlinear control canonical form. Then we don't have integrator chains as the corresponding system models. Now what to do then? What we could do then is we could specify a control strategy that is avoiding the state space transformation that we used also for the pendulum example. And for that, we can define Lyapunov function candidates as they are, for example, specified in the book that I had advertised before. And instead of the original equivalent control strategy, we then have feedback control procedures which guarantee steady-state accuracy and isotopic stability by generalization of this Lyapunov function candidate. I don't want to go into details about this here because this would be a second presentation. In fact, the only thing is that the complete control strategy then consists of not the original equivalent control strategy plus a variable structure part, but it is usually some underlying, usually linear feedback controller plus a variable structure part. And the identical thing to what you had seen on the previous slides is we're specifying the Lyapunov function candidates and proving that the corresponding time derivatives are strictly negative, and this is something that has to be done in real time. Okay, let me come to the conclusions. The conclusions is what you see on the slide here. The prerequisite for all of these control approaches is that we have in a symbolic representation a dynamical system model. Usually this is generated from first principle by modeling approaches for mechanical or electromechanical systems, for example. We had to perform a parameter identification as the fundamental step and assume that I have the corresponding parameter values. And then we can handle the goal of asymptotic stability and the prevention of violation of either one or two-sided state constraints. And the interesting thing is the use of interval analysis throughout the complete work is being done in such a manner that we can evaluate the expressions in real time. Okay, and future work will either be extensions to predictive control strategies or to the dual task, namely to state and disturbance estimation. Okay, thanks a lot for your attention.
Just use 30 minutes. So we can take one or two quick questions.
On the first example, you presented some uncertainty on the control variables and parameters.
Yes.
Does it work if you have some uncertainties on the state parameter? For example, if your state is an output of a filter or an estimator.
Yes. It works as long as you can specify bounds for the errors in the state.
Yeah. So you have to set some.
Yes. You have to set some bounded errors, and then it is working. Okay, and this is, for example, what was included in the simulation for this inverted pendulum. They assumed that, yes, this interval here, the first interval, is the angular uncertainty, and we have a position uncertainty of 1 centimeter, for example, plus minus 1 centimeter. Okay, this is directly working.
Another question. Yeah, I just have a quick one. For this kind of study, I'm wondering if the sliding phase surface can be an interval.
Yes, it becomes an interval.
The sliding surface S.
Yes. In fact, it's no longer a sliding surface, it's a region that you want to obtain.
So this you get a sliding region.
Yes, it's converted from a surface to a region.
Okay, I got it. Thanks. Okay, thank you very much.